Hello guys, welcome to the online recitation class. So the recitation class will be pretty much like the class with Dr. Taha. So every week I will be posting a video where I will be solving some problems, and if you have any question then we can talk about it on my office hour. And if you give me some problems, then maybe I can also solve it and then post it on the video. Okay, so let's start. First, we will be focusing on Routh stability condition. So this Routh stability essentially just a method to determine the location of the poles, whether it's on the left half plane or the right half plane, or even imaginary. So it's a method that is really handy to help us to determine the stability of any system. So in the first problem, we have T of S expressed by this equation. So this is a closed loop system, and we want to determine the stability by the Routh table. So the poles are given by this polynomial s to the 5 plus 2 s to the 4 plus 3s cubed plus 6s squared plus 5s plus 3. So we start by composing the Routh table. First we make the table. So you start by writing s to the 5, s to the 4, and so on the first or zeroth column. The first row corresponds to the s to the 5. So s to the 5 has one coefficient, so we put 1 here. And then s to the 4 has 2, so we put 2. And then here we put the rest. So s cubed 3, and then 6, 5, and 3. So next we want to determine the row on the s cubed. So this is done by calculating the coefficients, which is as follows. So how do we get 0? So we get 0 by multiplying 2 and 3. So 2 times 3 is 6, minus 1 times 6, 6. So 6 minus 6 is 0 divided by 2. It gives you 0. For the next column, we do the same, but with this column instead of this. So to get 3.5, we compute 2 times 5 minus 1 times 3. So 2 times 5 is 10, minus 3 is 7. 7 divided by 2, it returns 3.5. So we have 0 on the first column. So we cannot continue to build the Routh table on the simple case because we have 0 on the first column. So to proceed, we replace 0 with epsilon. So epsilon is, you can say, it's just a small number which is greater than 0. So a small positive number can be anything. So we substitute 0 with epsilon, and then we can proceed with the Routh table for s squared. So s squared, we compute 6 times epsilon, so 6 epsilon minus 2 times 3.5 minus 7, so we get 6 epsilon minus 7 over epsilon, and then the next column is epsilon times 3 minus 2 times 0, so nothing is 0. You get 3 epsilon divided by epsilon, it returns 3. Okay, so next we proceed to the S. So we do the same. So this term multiplied by 3.5 minus 3 epsilon divided by this is equal to x, where x is written by this. So it can be simplified to this term. So it has polynomials, and the S0 is just 3, always the last coefficient 3. So next we need to check whether there is a sign change on the first column. To do that, we can substitute epsilon with any number which is positive and relatively small, say 0.1, then we substitute here 0.1, and then on this term with 0.1 can be shown that this is always negative, and on x it's always positive, so you can compute that very easily, and you see that this is positive, so this is positive, 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 but this term is negative, and on the x is positive, so there are two sign changes actually on the first column. So from the Routh table, it tells us that there exists two positive poles. So it means that the closed loop system is unstable. Okay, I hope this is easy to understand. If you have any question, you can send me email, or we can discuss it on my office hour. So that's the first problem. Let's move on to the second problem. Again, we want to check the stability of the closed loop system. Similarly, we have a 5-degree polynomial. We start the root table, so write S5, S4 the 0 column, and the first two rows we copy the coefficients from the polynomial, so 1, 6, 8 on the first row, and 7, 42, 56 on the second row. Just copy this to form the first two rows of the Routh table. And then the next step is to determine the root table for S cubed. So let's do this. So we'll multiply 7 and 6. 7 times 6 is 42, minus 1 times 42 is 0, divided by 7 is 0, so we put 0. Oh, we have another 0 on the first column. Similarly, on the second column, 7 times 8 is 56, minus 1 times 56 is 0, divided by 7 is 0 again. So we get 0 on the third row. To proceed with the root table, we need to do the following step. First, we take the row above the 0 row, so 7, 42, 56, and form a polynomial. So since 7 is the coefficient of s to the fourth, then the polynomial on this row is 7s fourth plus 42s squared plus 56 is equal to 0, because it's a polynomial. And from this, it doesn't matter if we multiply with non-zero coefficient, so let's multiply with 1 over 7, we get 1 s to the fourth plus 6s squared plus 8, which is much simpler than this polynomial. But since they are the same, this polynomial and this polynomial, then we can replace this row with 168. So that's another trick. So you can multiply any row with non-zero coefficient. So we can multiply this row with 1 over 7 to get 168. So we take the derivative of this polynomial with respect to s. We get 4s cubed plus 12s, and then we put this on the zeroth row. The new table is this. So 168, again we multiply this row with 1 over 7, we get the same 168. So 168, and then this polynomial, since it is 4s cubed, then on s cubed, which is on the zero row, it has 4, we put 4, and then 12. Next, we compute the coefficient on the s square. So this can be done by multiplying 4 and 6. 4 times 6 24, minus 1 times 12 is 12, divided by 4 is 3. Or since we can multiply any row with non-zero coefficient, then let's multiply this with 1 over 4. It's equivalent to 1 and 3, right? So again, we can multiply 1 and 6, minus 1 times 3 is 3, divided by 1 is 3. So do the same, we get 8, also 8. On the s, again we multiply 3 with 12 is 36, minus 3 times 8 is 32. So 36 minus 32 is 4. 4 divided by 3 is 4 over 3. The same with this. So 3 times 3 is 9, minus 8 is 1. 1 over 3 is 1 over 3. And on the S0 is says 8. So either table is correct. So the trick here is, if you can simplify each row, then do it to make your life more simple and easier. So from both tables, we can see that on the first column there is no sign that has been changed. So we can say that the closed loop system is stable. So that's how you use the Routh table. So on the first problem, we have done an example where there is 0 on the first column, and on the second problem we do a problem where there is 0 on a row, so 0 on first and second column on this case. So I hope you guys can understand what I've been saying, and if you have any question, then send me email or ask me on my office hour. Okay, so let's move on to next problem. Problem 3. So this problem is asking for which k that makes the closed loop system is stable. So let's call this block as g of s. Since we have a unity feedback gain with negative feedback, then the closed loop system is g of s over 1 plus g of s. This is equivalent to k over s cubed plus 18s squared plus 77s plus k. Next, we construct a Routh table. So table is given by this. So s cubed is 1, put 1, 77s, so 77, and s square is 18 and k. So the next step is to find x, which is 77 times 18 minus 1 times k, so 77 times 18 minus k over 18, so x is equal to 77 minus k over 18, and on this term is just k. So for stability we need positive coefficients on the first column. Obviously we can directly see that we need k to be positive. We set k to be positive, that's the first condition, and the second condition is x to be positive, which is equivalent to 77 minus k over 18 greater than 0. This is equal to k to be less than 77 times 18, or k less than 1386. So in conclusion, to stabilize the closed loop system, we need k to be inside this set. So k will be a positive real number which is less than 1386. So that's a pretty simple problem. Next, we move to problem 4. It is a similar problem compared to the previous problem. So we want to find k such that the closed loop system is stable. Again, first we construct the closed loop transfer function. It's given by ks plus 2k over s to the 4th plus 3s cubed minus 3s squared plus k plus 3 times s plus 2k minus 4. The next step is to build the Routh table. Again, we have on the first row we have 1, minus 3, and 2k minus 4. Second row is from s cubed, so 3 and k plus 3, and then for convenience we put 0 on this term. Okay, the next step is to determine this constant right here. So we multiply 3 with minus 3, so minus 9 minus k minus 3, so minus k minus 12 over 3, and on this term is 3 multiplied by 2k minus 4 minus 1 times 0, so just 3 times 2k minus 4 divided by 3 is just 2k minus 4. Okay, the next step is to determine this constant. We call it x. So x, following a similar process, so multiply this term by this term minus this term times this term divided by this term. So this is x. So you can do this simple algebra to get this. So x is equal to k times k plus 33 over k plus 12. Okay, again for stability we want to find k such that the first column is positive. So first from this term next to s squared we need this to be positive, so k plus 12 must be negative, or k must be strictly less than negative 12. That's the first condition. Second condition, from the coefficient x which is next to s1, so obviously we need x to be positive. This is equivalent to k to be greater than negative 33. The last condition requires us to have 2k minus 4 greater than 0, which is equal to k greater than 2. So we can see that since from the first condition we need k to be less than negative 12, but on the third condition we need k to be greater than 2. So there is no k that can satisfy the first and the third condition. So we can conclude that the system cannot be stabilized. So since there is no k that satisfy the three conditions. So that's our conclusion. Okay, the final problem, problem 5. Again, we want to find k that stabilizes the closed loop system, but this time we don't have a unity feedback. Instead, we have another form of feedback transfer function. So let's call this block as g of s and this block as h of s. The first step is to form the closed loop transfer function. So the closed loop transfer function is g of s over 1 plus g of s times h of s. So after simplification, we obtain this form where the poles are given by this polynomial s cubed plus 2s squared plus k plus 1 times s minus k. So for stability, we only focus on the denominator. We construct the Routh table. On the s cubed is 1, and then on s k plus 1, so 1, and k plus 1, s squared is 2, 2, and minus k. On the s1, here is 2 times k plus 1, so 2k plus 2, minus k, so plus k, so 2k plus 2 plus k, which is 3k plus 2 over 2, and on this is just minus k. For stability, we need to have the first column to be positive. So from this, minus k to be positive is equivalent to k to be negative. From this coefficient next to s1, we need to have 3k plus 2 to be positive, which is equivalent to k to be greater than negative 2 over 3. So that x is k that stabilizes the system. So k must be inside this set. So k should be between minus 2 over 3 and 0. So k must be between these two numbers. So that's our answer. Okay, so we have solved 5 problems so far. So this is the end of our class. If you have any question, then send me email or we can discuss it on my office hour. Thank you guys.